Today's lesson is going to be about the pH concept. The pH concept is based on the autoionization of water. What does that mean? The autoionization of water, if we break that down into auto meaning self, ionization, we want H2O to be able to break down into ions. How does that happen? Because we know that water is a molecule and molecules aren't made up of ions. Well, if we think back to our last lesson on Bronsted-Lowry acids and bases, if we had two water molecules react, one of them would be the acid by donating a proton, and the other would act like the base by accepting a proton. And what we'd wind up having are these hydronium and hydroxide ions. Again, the hydronium ion is oftentimes abbreviated simply with a hydrogen ion symbol, but we know that there are no actual hydrogen ions floating around in the water. Those ions attract to a water molecule and form the hydronium ion. And that, my friends, is the autoionization of water. Water does do this all by itself, although as you could predict, not so much. If you think back to when we did our demonstration on electrolytes versus non-electrolytes, testing water proved that it was a non-electrolyte. So there aren't ions in the solution, or are there? There really are ions present, just not enough. We can do a mathematical calculation to figure out just how many ions are present in water, and that is given to us by this formula here. Next unit, equilibrium, we will spend more time learning about what this capital K means, but the little w after it means this autoionization constant for water. And what I'm able to measure are the concentration of the ions. That's what these brackets mean. When you see those brackets, it means concentration. And that concentration is going to be measured in molarity. Friendly reminder that that's telling you how many moles of solute are in your liters of solution. So this constant is equal to the concentration of the hydrogen ions times the concentration of the hydroxide ions. And after multiple experiments, chemists discovered that it's always equal to the same value, 1.0 times 10 to the negative 14th. If we know the number for the constant, we can then figure out what the hydrogen ion and the hydroxide ion concentrations would actually be. Take a second to do the math. For those of you who are a little stuck how to get started, what we want to do is give ourselves a scenario where this 1.0 times 10 to the negative 14th, we know that that's equal to the hydrogen ion concentration and the hydroxide ion concentration. I don't know what those values are, so I'm going to say X. The reason why I can say it's an X for both of them is because they're in a 1-to-1 mole ratio. So ultimately, 1.0 times 10 to the negative 14th is equal to 2x squared. Solving for x, I'll need to take the square root of 1.0 times 10 to the negative 14th. And my math will tell me that the hydrogen ion concentration and the hydroxide ion concentration will both be equal to 1.0 times 10 to the negative 7th molarity. Let's look at some more data before we link this up with the pH scale. Here we have some data. Data on the two left columns is comparing the hydrogen ion to the pH value. And the data in the two right-hand columns is measuring the concentration of the hydroxide ions and this thing called pOH. What patterns do you notice? Great. As you look at the exponents of 1 times 10 to a number, the positive of that value, the power, is our pH. 1 times 10 to the negative 12th, the pH is 12. Similarly, when I look at the concentration of my hydroxide ions and it's 1 times 10 to a power, the positive of that power is the pOH. So the relationship between the concentration of the ions and the P of that is logarithmic. Yes, your friend and mine, logs. So pH. By definition, pH is the measure of the amount of hydrogen ion concentration in a solution. We've been introduced as well to pOH. How would we define pOH? That's a measure of the amount of hydroxide ions in a solution. As we've learned, the pH scale is a number line where 0 or 1 will be our lowest, 14 will be our highest, and 7 is right in the middle dividing them, and that's given the special term called neutral. Any numbers less than 7 are considered acidic. Any number greater than 7 is considered alkaline or basic, or basicity. So a low pH value means that we'll be somewhere down here. It means that we have a high concentration of hydrogen ions because we're very acidic. A high pH value, that would be somewhere in this upper region of 12, 13, and 14, means we have a low hydrogen ions, very few at all. In other words, it's a basic solution. Note my color coding. I chose red for acid because that's the color that it turns litmus paper. And I chose blue for base because that's the color bases turn litmus paper. So how is it that these are related? Well, pH is equal to the negative log of the hydrogen ion concentration. We saw some examples of that, right? We said if my hydrogen ion concentration was 1.0 times 10 to the negative third molarity, what would my pH be? Well, we would notice the pattern that it would be the positive of what my power is. So I know my answer is going to be positive 3, but how did I get there mathematically? I literally took the negative logarithm of that value. And we're all allowed to use scientific calculators to help us solve these problems. And you're literally going to plug in the negative sign, the log button, and then 1.0. And instead of typing in times 10, let's please remember that the calculator has that EE or EXP button. And then you'll punch in the power of negative 3. And that will get you an answer for a pH of 3. Let's try another practice problem. What if my hydrogen ion concentration is equal to 1.0 times 10 to the negative 7th? Oh, that's a familiar number. It's the concentration of the hydrogen ions based on the auto-ionization of water. So if I want to know what's the pH, I'm going to substitute in to my formula. pH is equal to the negative log of my hydrogen ion concentration. In this example, the hydrogen ion concentration will be 1.0 times 10 to the negative 7th molar. Punching in negative log 1.0 -7 into the calculator, we're told that the answer for our pH value will be 7. Cool beans! That's the pH of water. Going to the other side, the other ion that's in water, again, our pOH scale. We got this definition down before. Let's indicate what our pOH scale will be. Again, our highest value will be 14. Our lowest value will be 0 or 1. And in the middle, we'll still have 7. Where do you suppose bases will be found on the pOH scale? You're right. Bases on the pOH scale are going to be values less than 7. Here's where we find our bases. Because on the pOH scale, having a low pH means you have a high concentration of the hydroxide ions. Acids will be those numbers greater than 7. Because on the pOH scale, a high value means low hydroxide ion concentration, meaning we're an acid. What do you suppose we'll call the pH of 7? You got it. It's still neutral. Let's repeat the calculation for the pOH concentrations. We said earlier that the hydroxide ion concentration in water was 1.0 times 10 to the negative 7th. What would the pOH value of that concentration give us? According to the formula, pOH is equal to the negative log of the hydroxide ion concentration. Substituting in the value of 1.0 times 10 to the negative 7th molarity, punching that into the calculator, negative log 1.0 EE negative 7 gives us the answer of 7. The pOH is 7. Looking back here, on our pOH scale, 7 is neutral. The only substance that's neutral is water. So if we take a look at the pH scale one more time, or the pOH scale, I prefer the pH because it is more common, and it's a nifty little way to think about this. If we have our number 7 as our middle point, I'll go with whatever, and I write water as HOH. Here's my hydrogen ion. To the right is my hydroxide ion, and that's also going to lay out where we have our acids and bases. To the left of 7 on the pH scale is where we have acids, and to the right of 7 on the pH scale is where we have bases. So water is our only neutral substance with a pH of 7 because it has a component of both an acid and a base. Mind blown. So is there a way that we can put all of this information together? Why, yes, there is. We started off talking about the auto-ionization of water and realizing that when we repeat these experiments over and over and over again, the combined concentration of the two ions that water breaks up into is a constant. That constant is 1.0 times 10 to the negative 14th. There is no unit associated with it. We learned the definition of pH, how it's measuring the concentration of the hydrogen ions in solution, and it's based upon a logarithmic scale. We learned about the definition of pOH, how that measures the hydroxide ion concentration in a solution, again, on a logarithmic scale. And finally, we've come to the conclusion that if I were to add the pH and the pOH of water, because that's what this is all based on together, we calculated the pH of water to be 7, the pOH of water to be 7. That total gives us 14. That's our upper end of the pH scale. At this point in time, please open up your homework assignment and work through the practice problems. Be sure to send me an email or pop into our virtual class meeting if you have any questions about the math.